Have you ever looked closely at your own hand? I mean, truly looked at it, not just as a tool that holds your phone or turns a page, but as a mystery that you carry with you every single second of your life. Hold it up for a moment. Let the light catch the ridges of your fingerprints, those tiny swirling valleys that are unique to you, written into your skin like a secret map. Press your thumb against your forefinger. Feel that sensation of pressure, of resistance, of solidity. It feels absolute, doesn't it? It feels like truth. You are here. The world is solid. The chair beneath you, the device in your hand, the air brushing against your face. It all feels so undeniably real, so filled with substance. But what if I told you that this feeling is a lie? What if the solidity you trust so deeply is nothing more than a ghost, a magnificent illusion conjured by something so small, so elusive that we aren't even sure it has a size at all? Tonight, we are going to drift past the surface of the world. We are going to close our eyes to the things we think we know and fall into the microscopic silence hidden inside your own fingertips. We are going to ask a question that sounds simple, but has kept the greatest minds of history awake in the dark. What is an electron actually made of? Is it a tiny ball of lightning, a wave of pure energy, a ripple in a cosmic ocean? Or is it something stranger, a mathematical point with no surface, no inside, and no end? So if you can't find a quiet space, let your shoulders drop. Let the tension of the day unravel like a knot gently loosening in water. Take a slow breath. Inhale the stillness. Exhale the noise. And come with me into the empty spaces between the atoms to find the ghost that holds the universe together. Before we begin, if these quiet journeys help you find a moment of peace in a busy world, a gentle like or a subscription would mean so much to me. It helps these stories drift further, reaching other restless minds, looking for a place to rest. Now, let's begin with the first mystery. Let's go back to that sensation of your thumb pressing against your finger. It feels like two solid objects meeting, like two stones clicking together. But physics tells us a different story, a story of vast, terrifying emptiness. Imagine we could zoom in on your fingertip. We drift past the ridges of your skin, diving down through the layers of the epidermis. We float past the massive lumbering structures of your cells, past the twisted ladders of DNA coiled tightly in the dark. We go deeper, smaller, until the biological world fades away, and we are left with the building blocks of matter itself. The atoms. You might remember the picture of the atom from your school textbooks. A friendly little solar system, a cluster of red and blue balls in the center, the nucleus, and tiny little dots orbiting around it like planets. It looks crowded, it looks busy, it looks solid, but that picture is wrong. It is a necessary simplification, a map that hides the true scale of the territory. If we were to see an atom as it truly is, the emptiness would make you dizzy. Imagine the nucleus of the atom, the heavy heart where the protons and neutrons live, is a single grain of sand floating in the middle of a vast cathedral. The dome of the cathedral towers high above, silent and shadowy. The walls are miles away, and where is the electron? The electron is a speck of dust dancing somewhere near the stained glass windows miles from that grain of sand in the center between the nucleus and the electron. There is nothing, no air, no light, no substance, just a void so pure and absolute that it makes the vacuum of outer space look cluttered. This is the shocking truth of your own body. You are 99.9% empty space. If we remove the space between the particles in your body, if we squeezed out all that emptiness and left only the actual matter, the entire human race, all 8 billion of us, would fit inside a single sugar cube. So why don't you fall through the chair you're sitting on? Why doesn't your hand pass through the table like a ghost, passing through a wall? If you're mostly emptiness and the table is mostly emptiness, you should glide right through each other without ever touching. The reason you don't is the electron, or rather the electron's ferocious need for personal space. This is where the story gets strange. The electron is not just a lazy planet orbiting a sun. It is a frantic, energetic ghost. It moves at speeds we can barely comprehend. Imagine a ceiling fan spinning on its highest setting. When the blades are still, you can easily put your hand between them. There is plenty of empty space. But when that fan is spinning at full speed, the blades blur into a solid disk. If you try to touch it now, you will feel a hard, impenetrable surface. The electron does something similar. It moves so fast around the nucleus, vibrating and probability jumping, that it creates a shell, a shield of energy. It isn't solid, but it acts solid. It defends the empty cathedral from intruders. But there is a second, deeper law at work here. A law called the Pauli-exclusion principle. It sounds technical, but it's actually quite poetic. It is the law of cosmic uniqueness. It states that no two electrons can occupy the same quantum state at the same time. They are fermions, the individualists of the particle world. They refuse to overlap. They refuse to share. When the electrons in your finger approach the electrons in the table, they panic. They sense the other electrons trying to occupy their space, and they push back with tremendous force. That push, that electromagnetic resistance, is what you feel as touch. You have never actually touched anything in your life. You have never touched your parents, your children, or your lover. You have only ever felt the repulsion of their electron fields hovering a microscopic distance away from yours. You are floating always on a cushion of quantum force, so the electron is the reason you exist. It is the architect of solidity. It creates the volume of the atom. Without it, the nuclei would collapse into a dense sludge, and the universe, as we know it, would vanish. But this brings us to the edge of the true mystery. We know what the electron does. It pushes, it flows. It bonds, it builds the world, but what is it? If we could stop that spinning fan blade, if we could freeze the atom and pluck that frantic little ghost out of the air, if we put it on a table and cut it open, what would we find inside? This is where the physics we learned in school begins to crumble. Because when we look inside the proton, the heart of the atom, we find things. We find 3 quarks swirling in a dance of gluons. We can smash protons apart and see their inside spilling out like the gears of a broken watch. But the electron resists. For over 100 years, we have smashed electrons together. We have fired them at targets. We have trapped them in magnetic bottles. And every single time we find nothing, no quirks, no gears, no smaller parts. As far as we can tell, the electron is not made of anything else. It is fundamental. It is a bottom layer of reality. But how can something be real if it has no parts? How can it have mass? How can it spin? How can it carry a charge if it has no size? Is it a point, a zero, dimensional dot? Imagine that for a second, an object with a zero radius. If it has zero radius, it has zero volume. And if it has zero volume, then its density, its mass divided by its volume, should be infinite. A singularity, a black hole. Yet the electron is not a black hole. It is light. It is swift. It is everywhere. This is the paradox that keeps us up at night. We are built out of bricks that have no size. We are made of ghosts that pretend to be solid. So what is it really? To answer that, we have to let go of the idea of things entirely. We have to stop thinking of the universe as a box of marbles and start thinking of it as something else, something more fluid, something more musical. We have to travel back to the moment the electron was first discovered to see how our understanding of reality shifted from hard matter to invisible fields. It is a journey that starts in a dark laboratory in Victorian England, with a glowing green tube and a man who thought he had found the smallest piece of the universe. But he had only found the first layer of the veil. The electron is not just a particle. It is a doorway, and to walk through it, we must leave our common sense behind. Take another breath. Feel the air filling your lungs. That air is made of nitrogen and oxygen atoms, billions of them, and around every single one of those atoms, electrons are dancing their frantic, silent guard duty. They are keeping the atoms of the air separate from the atoms of your lungs. They are capturing oxygen, trading energy, powering the beating of your heart. You are alive because of this mystery. You are thinking these thoughts because electrons are flowing down the neurons of your brain like sparks running along a fuse. You are a symphony of electrons wondering about themselves, and the silence you hear now, that is the sound of the universe waiting for us to ask the right question. So let's ask it. Let's go deeper. Let's peel back the skin of the world and look at the gears turning underneath. Our journey into the heart of matter is just beginning, and the first stop is a question that changed everything. If the electron is a particle, where is it? The answer, as we will see, is nowhere and everywhere all at once. We drift now toward the past, to the flickering candlelight of the 1890s, to a time when atoms were thought to be unbreakable spheres, the final word in creation. But in the shadows of a laboratory in Cambridge, a ghost was about to appear in a vacuum tube, a ghost that would shatter our reality forever. That is where we turn next. The year is 1897. We are standing in the damp, cobblestone streets of Cambridge, England. It is a time of gas lamps and horse-drawn carriages, of heavy tweed coats, and the smell of coal smoke hanging low in the evening mist. But inside the thick stone walls of the Cavendish Laboratory, the air smells different. It smells of ozone. It smells of hot copper and sealing wax. It smells of the future waiting to be born. At this moment in history, humanity felt a certain arrogance about the universe. Many physicists believed the great book of nature had already been written. We understood gravity thanks to Newton. We understood light and magnetism thanks to Maxwell. We understood thermodynamics. The famous physicist Lord Kelvin had even suggested that there was nothing new to be discovered in physics, only more precise measurements to be made. The atom was the bedrock of this certainty. The word itself comes from the Greek atomos, meaning uncutable or indivisible. For thousands of years, from the philosophers of ancient Greece to the chemists of the Victorian age, the atom was imagined as a hard, solid sphere, like a microscopic billiard ball, eternal, unbreakable, perfect. It was the final period at the end of the sentence of existence. You could build with it, but you could not look inside it because there was no inside to look at. But in a dark corner of the Cavendish lab, a man named J.J. Thomson was staring at a glass tube that would ruin this perfection forever. It was called a Crookes tube, a strange, delicate piece of scientific glass blowing. Imagine a glass bottle sealed tight with almost all the air sucked out of it, leaving a near-perfect vacuum. At one end, a metal plate called a cathode, at the other an anode. When you connected a high-voltage battery to these plates, something ghostly happened. A beam of light would stretch across the empty space. It wasn't fire. It wasn't a spark. It was a steady, eerie green glow that painted the glass at the far end of the tube. Scientists called them cathode rays but nobody knew what they were. Were they waves of light like the ripples in a pond? Or were they something else? Thomson was a quiet man, careful and meticulous, but he had a suspicion that the world was stranger than the textbooks claimed. He decided to ask the green ghost a question. He took a magnet, a simple horseshoe magnet, and brought it close to the glass tube. If the ray was just light, the magnet should have no effect. Light doesn't care about magnets. A flashlight beam doesn't bend when you wave a magnet near it. But as Thomson brought the magnet closer, the green beam moved. It curved. It bent away from the magnet like a stream of water pushed by a strong wind. Thomson watched the beam dance. He realized that whatever was flowing inside that tube carried an electric charge. It was negative. It was repelled by the negative pole of the magnet and attracted to the positive. Light cannot hold a charge. Waves cannot be pushed by a magnetic field in this way. Therefore, the ray was not light. It was matter. It was a stream of tiny fast-moving particles. But here was the problem. Here was the impossibility. The tube was vacuum-sealed. There was no gas inside to carry the current, and the metal electrodes were cold, solid matter. Where were these particles coming from? They were being ripped out of the metal itself. They were pieces of the atom, tearing loose and flying across the void. Thomson began to measure them. He calculated how much they bent, how fast they moved, and how much energy they carried. And when the numbers finally settled, they revealed something that seemed insane. These particles were light. Impossibly light. They were almost 2 zeros. 0 times lighter than the lightest atom known to science, the hydrogen atom. Imagine you are holding a bowling ball. That is the hydrogen atom. Now imagine chipping off a piece of dust from that bowling ball. That dust speck is the particle Thomson found. He called them corpuscles. We know them today as electrons. Do you understand the weight of this moment? For the first time in human history, the uncutable had been cut. The solid billiard ball of the atom was not solid at all. It was a container. It was a cage holding thousands of these tiny buzzing corpuscles. Thomson had discovered the subatomic world. He had peeled back the skin of reality and found a finer grain underneath. The news shocked the scientific world. Some thought he was joking. Some thought his experiments were flawed. How could matter be made of things that were practically weightless? If these electrons were so small, what filled the rest of the atom? The hard, comforting floor of Victorian physics had fallen away, and underneath was a confusing, swirling deep. Thomson tried to make sense of it. He tried to build a new picture of the world. He proposed a model that to modern ears sounds almost culinary. He imagined the atom not as a solar system. That idea would come later, but as a pudding, the plum pudding model. He suggested that the atom was a positively charged sphere of dough, a vague, spread-out cloud of energy, and the tiny electrons were stuck inside it like raisins in a Christmas pudding, floating, suspended, balanced in a soft electrical soup. It was a gentle image, a stable image, but it was an image of a world that was soft, permeable, and filled with thousands of tiny particles. It meant that the chair you sit on, the water you drink, the air you breathe, everything was made of this electrical pudding. Think about that for a moment. As you lie here, look at the device you are using to listen to this story. Maybe it's a phone with a glowing screen. That screen is the great-grandchild of Thomson's tube. Every pixel that lights up is triggered by the flow of electrons. We have tamed the ghost. We have taken the green phantom from the Victorian laboratory and taught it to paint pictures of our families, to send our words across the ocean, to play this very voice into your ears. The electron is the worker bee of the modern age. It runs our cities. It beats in the silicon hearts of our computers. but in 1897 it was just an anomaly, a glitch in the theory of the world. Thomson's discovery did something else, something deeper than just identifying a particle. It broke the seal on the mystery of stuff. Before this, matter was just matter. A rock was a rock. Gold was gold. But the electron showed us that matter is actually electricity in disguise, that the hardness of a stone is just a balance of charges, that the universe is not made of solid things, but of forces held in precarious balance. It was the first step into the quantum realm. Though they didn't know that name yet. They had found the grain of sand, but they had not yet seen the cathedral. Imagine the courage it took to publish that idea, to tell the world that everything they touched was an illusion made of swarming gnats. Thomson opened the door, but he didn't walk all the way through. His pudding model was safe. It was cozy. It kept the atoms solidish. It kept the universe filled. He didn't know yet that the dough of his pudding didn't exist. He didn't know that the positive charge wasn't a soup, but a bullet. He didn't know that the emptiness was coming. The electron was just the first domino. And as the 20th century dawned, a student of Thomson's, a boisterous, loud-voiced man from New Zealand named Ernest Rutherford, was about to knock over the next one. And this time, the model wouldn't just shift. It would explode, the pudding would vanish, and the terrifying void would take its place. But for tonight, let's stay with the corpuscle. Let's stay with the green glow in the glass. Close your eyes and imagine that stream of silent fire bending under the magnet. Imagine the realization washing over you. I am not one thing. I am a swarm. You are a colony of billions upon billions of tiny sparks, held together by nothing but mutual attraction. It feels fragile, doesn't it? To know that your solidity is just a temporary agreement between particles. But there is beauty in that fragility. It means you are dynamic. It means you are energy. It means you are electric. As we leave the Victorian lab, blowing out the gas lamps and stepping back into the fog, we carry this new knowledge with us. The atom has parts, the world is divisible, and the smallest part of you is a thing that loves to move, loves to flow, and refuses to sit still. But if the electron is a particle, a tiny ball of negative charge, then it must be orbiting something, right? Like a planet orbits a sun, that is the picture we all learned. The classic solar system atom, it is elegant. It is beautiful, and it is completely spectacularly wrong. Because if an electron were really a planet orbiting a nucleus, something catastrophic would happen in less than a fraction of a second. The universe shouldn't exist. You shouldn't exist. Every atom in your body should have collapsed into a burst of light billions of years ago. Why didn't they? What stopped the crash? To answer that, we have to watch the solar system model die. We have to witness the birth of a new kind of physics, one where rules like position and speed stop making sense. That is where we are going next into the catastrophe that saved the universe. So settle in. Feel the weight of your body on the bed. That sensation of electrons pushing against electrons. A silent, microscopic high five that keeps you from falling through the floor. Let the green glow fade. The real mystery is about to begin, because the electron isn't just a piece of dust. It's about to become a wave. We have arrived at one of the most dangerous moments in the history of thought. We are leaving the Victorian era and stepping into the early 20th century, a time when the comfortable furniture of the universe was being rearranged piece by heavy piece. We have discovered the electron. We have peeled it off the atom like a loose thread. And now, thanks to Ernest Rutherford, the loud New Zealander who loved to smash things, we have discovered the nucleus. Rutherford had fired alpha particles at a thin sheet of gold foil. expecting them to punch right through J.J. Thomson's plum pudding, like bullets through mist. Instead, some of them bounced back. It was, he said, as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. That bounce changed everything. It meant the atom wasn't a soft pudding. It had a hard, dense, tiny stone in its center, the nucleus. And suddenly, the picture snapped into focus. The picture we all know, the solar system model, a heavy sun in the middle and tiny electron planets orbiting around it in the vast empty dark. It is a beautiful image, isn't it? It feels right. It feels symmetrical, as above, so below. The structure of the atom mirroring the structure of the galaxy. It suggests a deep hidden harmony in nature, a single blueprint used for the smallest speck and the largest star. We want it to be true. It comforts us to think that we are made of tiny solar systems, but the universe, as it turns out, does not care about our comfort. And this beautiful solar system model contained a seed of destruction so potent it should have ended reality before it even began. Here is the problem. It lies in the laws of electricity and magnetism written down by James Clerk Maxwell decades earlier. These laws are the bedrock of our technology. They explain how your phone works, how radio waves travel, how light shines, and they are very strict. One of these laws states that whenever an electrically charged particle accelerates, that is, whenever it changes its speed or its direction, it must give off energy. It must radiate light. Think of a radio antenna. We shake electrons up and down inside the metal rod, and they spit out radio waves. We force them to move, to change direction, and they pay for that motion by losing energy. Now look at the electron in Rutherford's solar system. It is orbiting the nucleus. Even if it is moving at a constant speed, it is constantly turning. It is moving in a circle. In physics, turning is a form of acceleration. You feel this when you turn a sharp corner in a car. Your body is pulled to the side. That pull is the feeling of acceleration. So the electron is accelerating according to the ironclad laws of Maxwell. It must be radiating energy. It should be glowing. It should be screaming out light as it curves through the dark of the atom. But energy is not free. If the electron is giving away energy as light, it must be losing it from somewhere else. It must lose speed. It must lose altitude.